Hello. Today we are going to discuss about vectors which are included in the portion that is motion in a plane. Of course, the vectors can be directed along a single direction, but nevertheless they can be considered on a plane as well. And so basically what vectors mean, as you might have studied previously, are those quantities which have a magnitude as well as a particular direction of motion. If the direction is properly defined, then you can call the quantity to be a vector quantity. But in case the direction is not really clearly defined, then it may not be a vector quantity, as in case of electric current, where you have a direction of flow of current, but nevertheless it has no direction of its own. It is directed along the channel provided, that is the conducting medium that has been provided. So likewise, if we consider something to be a vector quantity, it independently has a direction of its own. Now, so any physical quantity having magnitude and direction is known as a vector and usually represented uh, by an arrow. Now, this arrow that I have made over here, it has a starting point, let that be O, and an ending point, let that be A. Now this represents the a certain vector. Let us suppose say this is the A vector. Now this A vector that I have represented over here, OA gives the magnitude. OA, the length, gives the magnitude. So if we are to represent a vector, we represent it by a certain magnitude. Now half of this vector, if I say that I have a vector which is half of a vector, then obviously it will be directed along the same line, because the vector has a fixed direction of its own, but the magnitude is halved. So if OA is the length, we can almost, I can draw another line of the same length and directed along the same line, so it represents the same vector, A vector, but the midpoint to that, if I represent another vector, let us suppose say OB vector, now which gives me the magnitude, which has the magnitude of B. So this B vector is equal to half times of the A vector, where A vector was obviously OA. Now this is how we represent a vector which has a tip, which is particularly known as the head, which is represented by A over here, and a tail which is represented by the point O, that is the starting point of the vector. Now we, as we discuss about vectors, we can tell about its representation. Now as you can see that I have represented this B vector and the A vector by topping it over with an arrow symbol. Now this arrow represents a vector quantity. Usually what you find is in books, in many books that you will be studying in higher physics, what happens is that they usually do not represent a vector with an arrow over the variable which represents the vector. They usually just mark it in bold writing. So suppose the B or the A is written in bold, then that also represents a vector as well. So in most of the books, you may refer to the notations that they would have uh, represented right from the very beginning of the books. So it's not necessarily that, usually it is ideal to represent the vectors by the arrow over the variable whichever represents the vector. But in some books or in many higher physics books, you will find that the vectors usually are represented by bold letters. Okay, now we will be considering some of the types of vectors. Now, there are many types of vectors actually. So the types of vectors that we are about to discuss, they carry a term which is known as, to start with, we have the equal vectors. Now, what do you mean by the term equal vectors? Now, obviously, two vectors will be equal if they are equal in magnitude as well as in direction. Now, if you observe this thing, this vector, suppose I say this is a vector, which is, suppose I say this is a vector, and I have another vector which is the b vector. Now, as you can see, if I consider the starting points, I just represent the starting points by a dotted line which connects them exactly perpendicularly. Okay, so and the ending points as well. I hope you understand this, because the vectors must have equal magnitude. Now, equal magnitude, usually the magnitude is represented by the length, as I have mentioned previously, that length of a vector that we are representing gives the magnitude of it. While the direction, obviously these two lines, as you can see, are parallel, so they are directed along the same direction. Not exactly in the same line though, but they are directed along the same direction, that is from the left towards the right hand side of your video. So in that case, both the vectors can be termed to be as equal vectors, while in the other way we have the negative vectors. Now, in case of negative vectors or negative of a given vector, suppose I have a vector c over here which is exactly having the same magnitude as that of A or as that of B. Let me draw it correctly. Okay, you can actually cancel that. We will do away with it because there was scribbling over there. So now if I look at this C vector that I have drawn below that uh, cancelled one, so that represents a negative of the other vectors which were equal. Let it be, suppose, say A or B. So C vector here is, let me take the first one, that is A. So C vector is the negative of A vector. And how do we know that? Now, negative in the sense of direction, that is, C is directed exactly opposite to that of A while having the same magnitude as that of A. If you again consider the length of C, it is equal to that of A or even B. Now, B, since we have represented to be the equal vector as that of A, so C can be also the negative of B vector as well. So this is what we consider as a negative vector. Now, if we look at a third type, we have uh, a zero vector or a null vector. Zero or null vector. Now, many a times during vector addition, vector calculations, the operators that act, you have the result of the magnitude to be zero, even if there is certain direction that you can give to it. Where the magnitude goes to zero, we'll be looking at some of the examples, but where the magnitude goes to zero is what we call it, we represent as a zero or a null vector. Now, this magnitude can go to zero while multiplication of two vectors, where later on we will be looking at the multiplication of vectors, that is the scalar multiplication as well as the vector multiplication. And the vector multiplication that we will be looking at has a direction of the product vector, and sometimes the magnitude in that case can go to 0, and we are left with only the direction. So in that case you have the direction but not the magnitude, so the resulting vector or the product vector is simply termed as a null or a zero vector. Now the next thing that we will be discussing is a position vector. Now position vector, obviously, as the name suggests, it gives the position of a particular point or an object, whatever it may represent. But I think prior to position vector I must discuss about the unit vectors. So let me write down unit vectors. Now the unit vectors give the unit value to a vector. Suppose I say that I have the three coordinates that are available, that is the in the three-dimensional space I have x, I have the y and the z axis, and the popular unit vectors that we take are along these axes, that is having a magnitude of unit value. Let us suppose say this goes up to 1, so this is the unit vector which is directed. This is a vector represented by that arrow that I have just drawn, and from the origin the magnitude is represented by those curls that I have given below it. So this is a unit vector along the x direction, and it is usually termed as I hat or I cap. And similarly you have the unit vector along the y direction, and that is j cap. And finally the unit vector along the z direction is k cap. Now obviously the magnitude in this case is unity or 1. Any given vector a, suppose a is a vector, and this vector can have a magnitude as well as a direction. So let me say that this a mod is the magnitude, while the direction is any random direction selected as a cap. If it happens to be along the x direction, it is I cap. If it happens to be along the y direction, it is j cap. If along the z direction, it is k cap, or any random given direction, it will have a magnitude of only 1. So a cap is that unit vector. So how do we represent that unit vector? Now representing a unit vector is quite simple. All you need to do is to divide the given vector with its magnitude, which is what I've done. A cap is the unit vector for a when it is divided with its own magnitude. So all you are left with the magnitude as having the value 1, and the direction remains intact, that is along the a cap direction. So now if we are to represent a particular object or a particular point, let us say, let that point be a point P, and along the x, y and z coordinates we represent the position of that point. It has the coordinates to be equal to, let us say, x, y and z in small letters. Then we can represent the position with respect to a fixed point, here the fixed point being the origin of the coordinate system. So this vector which gives or represents its position of the point P with respect to the with respect to a fixed point, that is the origin of the coordinate system, is what we call as the position vector. So OP here is the position vector and of the point P, and OP can be represented in terms of x, y and z because it has traveled a distance x along the x direction, where the unit vector is I cap. So it has a magnitude of x along the x direction, and the direction is obviously I hat or I cap. And similarly, along the y direction, it has traveled through a distance y, having the unit vector along that line to be j cap. And finally, along the z direction, it has moved through a distance z, having the direction to be represented by k cap. So this entirely represents the position vector of the given point with respect to the origin of the system. Likewise, we can have the position vector with respect to any other point, provided we know the parameters that are involved or the coordinates that are involved. Now, as in case of the position with respect to another point, we can say that suppose we have displaced a point object. We have displaced a point object where we have the x, y and z coordinates again, and we take first point and we have displaced this quantity, whatever it was, from the point A to the point B over there, and the displacement is along that line, so that line gives me the displacement vector. So the sixth one that we are discussing right now is the displacement vector, and the displacement vector gives the obviously it gives the displacement from the initial position to the final position, here the initial point being A and the final point being B. So we have the position of the point A and we have the position of the point B. From there on, we can obtain the value of this position vector. However, this value will be much easier to calculate when we get to know about the addition of vectors later in this chapter. So these were the various types of vectors. There are actually, you can have many such types, because you have the unequal vectors, which are obviously not the equal vectors. You have the opposite vectors, which are somewhat the negative vectors but not exactly the negative. You have the parallel vectors, where equal vectors are always parallel, but parallel vectors cannot be of, may or may not be of the same magnitude. So you have parallel vectors, you have opposite vectors, you have anti-parallel vectors, and you can have many more such types of vectors that you can say, but they all come under the category of these vectors that we have defined just now. Some way or the other, they will be behaving like the ones that we have represented right now. So all equal vectors may not be all equal vectors are parallel vectors, but all parallel vectors may not be equal. Because if I consider the case of parallel vectors, let us say the seventh one, I write it as parallel. Now in case of parallel vectors, what we have is that both the vectors will be directed along the same line, of course. Let this vector be A and let this vector be, suppose, B. In both these cases, we have A to be along the same direction as that of B, or B to be along the same direction as that of A, but never will they be equal in magnitude. The magnitudes of A and B in this case are not the same, and that is why they are just parallel but not equal. However, two equal vectors that we just represented at the top, right there, two equal vectors, they are always parallel, but not all parallels are equals. Similarly, in case of anti-parallel vectors and negative vectors, so all negative vectors are obviously anti-parallel, but never is the case in the opposite way. That is, all anti-parallel vectors cannot be negative vectors. So these are some of the definitions or the types of vectors that we have discussed so far. We'll be discussing many more types of um, we'll be discussing many more, not the types, but many more things about the vectors, such as their addition, multiplication, and the operations that are involved with vector quantities. And we can from the addition part of it, we can define that displacement vector right there, the sixth one that we just discussed. So till then, thank you.